All right, last we talked, we were trying to remove the ambiguity from this grammar. Was anyone spooked enough to actually work on this over the last 24 hours, 23 hours?
I completely forgot about it. I'm sorry.
That's okay, me too. It's funny how every day is just it's an independent from the last day.
Right.
Yeah,
It's like severance.
exactly, exactly.
I mean, I had a thought, which was you could reclassify the non-terminals, a separate non-terminal for multiplication versus addition.
Yeah.
Um,
If we think of it in terms of a parse tree, we want to make sure that the higher order of operations happen lower in that parse tree, and that would be one way to do that, absolutely.
I was just gonna say that same thing, thinking of it as a parse tree and then having the things like parentheses be lower in the tree.
Yeah, yeah, and that way, when you're doing a depth first search, it gets resolved first before the higher up components. That is exactly what we have to do. So to make that work, we do it with something that looks like this. And this is a little bit strange. I'm going to take a little bit of a look at this just to see how this would work. But an E now is the left-hand side of an addition. The T is the right-hand side of an addition or the left-hand side of a multiplication. And F is the rightmost side of a multiplication or the result of a parenthetical expression. And then an I is now your terminal. And we can always go from higher precedence to lower precedence. But in order to go from lower precedence back to higher precedence, we have to incorporate parentheses. And that's the only way to prioritize addition over multiplication, is if we go from E to T to F to parentheses back to E. So that's how we end up forcing the parentheses to, but we allow for that to take precedence over something, is that it's a loop, but to get back to something that's higher, we have to go through parentheses to get there. And you can see that as we try to do that same plus times from before, using exactly the same parse tree idea, we get E plus T. And so now, since the T is the right-hand side of the addition, we have to incorporate that first. And that allows us to go do that multiplication before we do that addition. There's no way to do that in any other way. And even if you flipped the times and the plus, this will still work. And you'll still do the times before the plus unless there are parentheses. And the parentheses become the only way to override that order of operations. I feel like it's worth staring at it for a little bit longer just to get that sense of why does that work? Try to work through that in your mind. Why would you need parentheses to work around that?
I think it's initially confusing because there's expressions where the E plus T and the T times F.
Right.
My immediate reaction would be thinking that should produce something very messy. So, but like the more you think about it, you realize no, it tracks. Like it makes sense that you do it this way.
Yeah, I think it's worth sitting down and thinking about for sure. At some point, spend 15 minutes looking at this. I feel like that's a little outside of how much time we can reasonably spend in class going over it, but there's something to be said there.
Is this the most efficient way to do this grammar?
Yep.
Okay.
So it's not necessarily something that I expect people to generate, but if you play around with it, you'll start to realize what some of the dead ends are, why certain grammar or certain ways won't work. What's unfortunate though, is there is no efficient algorithm to be able to answer whether a grammar is ambiguous or not.
So it's just an intuition thing.
Yeah, kind of. You can either show an example where it is ambiguous, but there's no easy way to prove that it is not ambiguous. You basically have to iterate over an infinite number of possibilities and say, well, that's not ambiguous, or at least I can't show that that's ambiguous. I can't show that that's ambiguous. I can't show that that's ambiguous. Does that mean it's not ambiguous? No, you just haven't found the example yet, but there are an infinite number to consider. And possibly an infinite number of paths through the grammar to be able to try to show that it is ambiguous for any particular one. So yeah, it relies on a very intuition heavy argument to be able to show. So it's often on people to try to rewrite grammars in ways that don't have it, but we have no way to prove that we don't have ambiguity in the grammar that we generate. Until someone points it out. But annoyingly, ambiguity can be baked into languages and not necessarily grammars, to the point where you cannot create an unambiguous grammar for it, because the language by its nature is ambiguous. Let's give you an example for that. So, first question I might have for this language, A to the N, B to the N, C to the M, union A to the N, B to the M, C to the M. This tells us that there are either the same number of A's as B's, or the same number of B's as C's. Or both. So the question is the language context free? If the language is context free, we should be able to come up with a context free grammar for it. Take a little bit of time and see if you can come up with a context free grammar for this. Wouldn't get really mad over there.
It's a lead fellow with that.
Oh.
So when I wiped it on, smeared.
I thought someone was just like, damn it, Josh. That would make sense too. Not a challenging one to come up with a grammar for, huh? Does anyone think this is impossible? Is this language not context free? Or does intuition tell us there might be a solution to this?
I feel like there is. But I feel like the solution that I'm thinking of is also contrived. And it would just be a lot of like non-terminals that are just like you could follow them and it would make sense, but it would just kind of be like the similar
Okay.
to the previous where there's just a lot of
Yes.
steps.
Okay, so one vote for, we think this is possible, but it might be a contrived grammar. Any other intuitive thoughts as to whether this is context free, not context free approach to a grammar?
Definitely, I don't think it's regular.
Yeah.
That's
It's definitely not regular. That's a good place to start for sure. kind of has a baked in A to the M, B to the M portion of it. Anyone else have some insights?
I've forgotten the definition of context free. Can I get a reminder?
Yeah, so this is just a grammar where we can use any terminals or non-terminals on the right-hand side. There's no restriction to the right-hand side of the grammar, kind of like the first homework's grammar problems.
Oh, okay.
So we have full freedom to express this in terms of logic.
I think my issue is that, like, you're not gonna know what side of the grammar you're on, like what one,
Yeah,
until you're done parsing the.
I was thinking the same thing.
what's beautiful about context-free grammars is we allow for non-determinism. So that's actually a great point for how you start this. We want to kind of build a grammar for the left-hand side and a grammar for the right-hand side. What can we do if we had separate grammars for the left-hand side and right-hand side? How could we combine them in a way that allows for a single grammar?
S goes to L vertical pipe R.
Yeah, S arrow L or R, sure. And now we just can proceed with what is the grammar for the left-hand side. That starts with its own start non-terminal L, and the right-hand side starts with its own start non-terminal R. Seems like a solid way to go about it. So let's see if we can do that. What is L going to be made up of? We need something that represents pairs of A's and B's and something that represents C's.
Yeah.
So let's just call this A and B. That's going to be kind of a little bit annoying, but A is able to make a single A and a single B, and between that we can recurse, or we cannot do that. But whenever we see an A, we have to see an associated B, and where we recurse is in the middle of that, so that we have at the end of that the same number of A's as B's. B is going to represent our C's, and it happens after all of these A's and B's. So B would just recurse into allowing for a C followed by more of them or none of them. There's nothing that says that N and M have to be different. Otherwise, we would have to account for that somehow, and that would make this a lot harder. But it's not, we don't have to. So this is the complete left-hand side. How would we handle the right-hand side similarly? We could say that right can go to CD. We don't want to use the same non-terminal variables that we have for that. But now we need to pair the B's and C's together. So C is going to produce nothing but A's. And D is going to produce pairs of B's and C's, very similar to how we did with the A's. So we will have B, capital D, C, or lambda. And that would get you there. So it's a bit contrived, but when you break it down into the associated logic steps, you start to see overarching idea broken down into component and component. And each of these components has an associated internal structure that can be broken down into component and component. Structure, component, component. So I like to see grammars like this as kind of, here is the kind of like title. Here is the definition. And within that definition, we have a subtitle and some sub-definitions.
You can kind of format a JSON file.
Yeah, it kind of is, right? And then we have another subtitle and some more definitions. So there's structure to the grammar in ways that breaks down and kind of makes it seem like objects or representable in a JSON or So I see the work that you all have done in your programming classes as preparation for how to think about designing abstract concepts. Don't necessarily see them as two very different things. They utilize the same underlying skill set of problem solving and problem decomposition. Thoughts on that? Does that make sense? We agree that this maps to this language?
Yeah.
Is there any way that we know as we're parsing the first character, when we see A, do we take L or do we take R? Well, it absolutely matters in terms of one of them is going to succeed and one of them is going to fail. But
in the context, string was just a.
right, non-deterministically, we can do both at the same time, but deterministically, how do we make this choice? You can't without looking at the rest of the string. So if we're trying to parse this in one path, this is why ambiguity is baked into this language. Because regardless of how you design any kind of machine for this, we have to explore it in parallel in order to be able to answer it. There's no way to explore this deterministically and know when we see the first character, which part of this union we're actually in. So that's the point we're trying to make on the slide, is that sometimes ambiguity is baked into the language itself. And that actually means that there's a difference in the expressivity of non-deterministic context-free languages and deterministic context-free languages. They're actually different classes of languages. And context-free language, context-free grammars can represent the equivalent of non-deterministic context-free languages. Whereas deterministic context-free languages is only a portion of that. We didn't see that in regular languages. DFAs and NFAs could represent the same class of language, but as we talk about context-free languages, that will no longer hold, which is kind of baffling as to why that is. So we had a left side of the union, a right side of the union, and then we can combine them. Then we see that A to the N, B to the N, C to the N has two different derivations, so the grammar is ambiguous. And then parsing it deterministically, we see that we don't know on the first character which path to take. So those are kind of all of the takeaways from this problem and this idea. So in general, no grammar can exist that does this deterministically, which is weird and cool, possibly annoying. So the goal of studying context-free languages, context-free grammars especially, is in the end to apply them to programming languages and to apply them to compiler design. But we've kind of somewhat already done this, and we can now take what we've learned about this and really show it being applied to programming language syntax. So as we've seen, we can define languages with a grammar. And languages themselves are often specified in a particular grammar form called BNF, Backus-Naur form. As an example, a grammar specifying addition and multiplication could be written as, and this is where the E and T and F come from. In the prior grammar, they're expressions, terms, and factors. So BNF just looks like this. The arrows that we've been drawing are just colon, colon equals. And we use the angle brackets that we saw in the part of the homework problem dealing with representing floating point numbers. So we saw that a little bit already, but it's just like the grammars that we've been seeing with these couple of changes. We see that we have terminals, the plus and times, the characters that you can actually type, and then more abstract ideas, terms, expressions, and factors that represent parts of the computation. And we see that, as I suggested to those of you who came to me in office hours about that question, that If non-terminals aren't just letters, but they represent some kind of idea, then it's best to utilize that idea as the name of your non-terminal, kind of like variable naming. As we do this, we see that we can start to make grammar segments that look like programming language syntax. So we have an idea of a while statement that can break down into the terminal, the keyword while, followed by an idea that is an expression that is the termination condition, or I guess the continuation condition for that loop as an expression that needs to evaluate as an expression. And then there is one or more statements. We should really represent this as one or more statements, but a statement representing what gets repeated as long as the expression remains true. But that is syntactically how a while statement is formed. It's made up of those components. And now we have the ability to determine whether a program is written syntactically correctly with regards to a while loop. We don't know if there is a logic error in that while loop or if that while loop ever terminates. Nothing about this grammar specifies the semantic meaning or the logic of what happens inside of this loop. It just says, does this syntax represent, is this correct for a loop? If the expression part of this isn't an expression. While 74, what does this mean? It's not a Boolean expression. Yeah. It's not 1 in C.
I think you could run that in JavaScript, while 24.
Yeah, you could run it in C as well. Anything non-zero is true when you create infinite.
Oh, yeah.
You can make some very confusing C syntax.
Well, I actually do that a lot, while true, and then later I just say,
Break.
return, break.
Yeah, yeah,
It's easier.
yeah, it's terrible design, but it works.
Well, you can't have like 50 different conditions in like the while, the head of the while. I feel like.
There's always an easier way. Or more readable way. But I find throughout undergrad, people do that a ton, and that's fine. So yeah, it's a simple grammar production, which is really cool. It looks like it's a simple grammar. There's a single terminal followed by 0 or more non-terminals. That's cool. And when we have keywords in programming languages like while or return or int, then they're great. They're visual structure to guide the program's reader, but they also make the compilers work easier because they become the terminals for representing ideas. On the other hand, we didn't have a simple grammar production for the expressions on the last slide. So a high-level question that we're not going to answer quite yet, we'll come back at the very end of this class and answer this question, is what kind of rules and grammars can we parse efficiently? If we had to place restrictions on grammars such that programmatically we could easily determine whether a string was in the language accepted by that grammar or not, as well as other complex questions associated with that, then how would we actually go do it? So that breaks down into LL and LR grammars, and that's the very last thing we'll cover in the class. After we've actually talked a little bit about compilers and how they work. But it is the most important part of putting together an efficient compiler, at least at the parsing step. Then the question I would have for you is, in general, what can we model with a context-free grammar associated with programming languages? What can it model? What is I've alluded to this with the language that I've used, but
Just the syntax, right? The parse tree, basically.
literally all syntax, yeah. But what's something that it can't model? I've also alluded to this. I need to stop thinking ahead.
Yeah.
Just go based off of the ideas that are on the slides.
Like the computation, the stack. Of
Yeah, it's semantic meaning.
procedure calls.
So something like this, is this legal syntactically?
Yeah,
Yes. Is it legal semantically?
no, probably not.
No. In most programming languages, and any that I am aware of, this is not something that we can do.
Right.
However, if we break down the syntax, we have a variable type, we have a variable name, we have the equals portion of an expression, and we have of an assignment, and then we have a value. So syntactically, it has all of the components of an assignment statement. It's just that the assignment statement is trying to do something that we don't want to allow, that has no meaning. But a grammar itself isn't going to catch that. So the answer is yes, it is syntactically correct. But we have semantic rules that deal with why we don't allow this. So we need an additional portion of compilation to go over semantic rather than just a context-free grammar. So we cannot express type clashes in grammars. So this is trying to shove a double into a character variable. Sometimes a compiler can handle this for us with some tricks. You try to say double D equals 4. I'm trying to put an int in a double. Can we do that? Usually we can. In Java we can. But there's an internal conversion that goes on from int to double before that is stored in the double variable. It's not something that you, the programmer, specify. It's something that the compiler handles underneath the hood. But it's because it's possible to do that. So semantics in general are harder than syntax, which is why we focus on syntax in this class more than we focus on semantics. But nothing as simple as just a context-free grammar exists for semantic analysis, unfortunately. But there's nothing actually out there that's universally accepted for it. So there are many design philosophies surrounding how to handle semantics. And they end up being kind of what's typically used is a top-down and bottom-up, meet in the middle kind of approach. We look at what each expression evaluates to, and then we look at the assignment type of what it's supposed to do and look at that point, is there going to be a type clash from that? But it involves us actually having to do computations lower in the tree to be able to identify that value. Because you said char C equals, some character plus some double. Now, what does that evaluate to? Is that a type clash? And that gets deeper and deeper in the tree as you try to figure out what can we do to different variable types? What can we store in certain variable types? And that will be a language-based decision for what is possible and what assumptions the language is going to make, if any. What is an error versus what is an assumption? So, ongoing discussion amongst computer scientists about how to handle the semantics problem. But we're going to hone in and focus mostly on syntax because there's still a lot there. I love my short slide decks. That's the next one. Way too many of these open for my own good. All right, we're going to dive into a pretty quick, very short 5-slide slide deck. Like I said, that includes the title slide. I like my short slide decks about simplifying context-free grammars. We're going to spend maybe 10 minutes on it. So last thing we talked about, membership and parsing, important. We looked at the feasibility of brute force parsing, and we determined that brute force parsing sucked. That was the takeaway from that in very technical language. The efficiency, again, a very technical term here, garbage. And the takeaway from this is we need to bake efficiency into this if we're ever going to hope to be able to answer the membership question. And I will refer to that concept of the membership question, which is just given a context-free grammar, is the string accepted? Is it part of the language represented by that grammar or not? That is the membership question. As we mentioned, CFGs, context-free grammars have no restrictions on the production construction. Yeah.
So by saying, trying to make trying to make CFGs more, efficient. Does that kind of mean that we're trying to make them unambiguous? Does that, what that mean?
It's part of the problem.
Yeah.
So the problem is just straight up unsolvable if they're ambiguous. We're not gonna be able to parse it in one pass. So we need to figure out how to change grammars. We also, there ends up being some forms of grammars that we need to convert grammars into. And there are nice, easy algorithms for doing that. So that is one of the next things we're going to learn after this. So can we restrict somehow the right-hand side of a context-free grammar production without necessarily reducing the power of the kind of language that it can represent? And still improve the efficiency of answering yes or no to whether some query string is a member of the language represented by that grammar. How would we do that? Let's first look at what can we do to grammars. So one thing we know, starting right off the bat, lots of different equivalent grammars that can generate the same language. In fact, an infinite number of equivalent grammars for any given language. You just add a bunch of or lambdas, or lambda, or lambda, or lambda, and you get the same grammar. So obviously there are an infinite number of them. You could create loops within your grammar that don't actually do anything. You can go from a non-terminal C to a non-terminal D, back to a non-terminal C, C to D to E to C. So again, an infinite number of ways to make this not have more expressive power, but just be more complicated. One thing we may want to be able to do when we do this is to remove whether we need to consider the empty string. So a simple rule just says there is a new start symbol. The start symbol goes to the old start symbol or lambda. And now we could write a grammar not worrying about whether the empty string is accepted or not. So this is a general rule to remove the concept of the empty string from the rest of the grammar. So now solve for S. Always works. We also have, we're going to call the substitution rule. If we have a terminal followed by a non-terminal followed by another terminal. So T sub K here, just some terminal. So T sub 1 is a terminal, T sub 2 is a terminal. N is some non-terminal. We can replace with all possible productions of that non-terminal. So as an example, we can just say wherever B appears on a right-hand side, because it is between a lowercase b and a lowercase c, we can just now create additional productions, replacing B with every definition for B. So all we've done moving from this is weird. Right where I want to draw it to. So this B is right here, so we're just gonna say insert that right there and insert that right there as two separate productions. So we see that this B was replaced with A capital A there, and this B was replaced with B there. And now this capital B appears nowhere in this grammar, so this rule is useless. It's an equivalent of grammar, so just remove it. So this is the substitution rule. As long as this non-terminal appears between terminals, then we can make this substitution without changing the nature of the grammar. As soon as there's a non-terminal on either side, it gets much more complicated. We have to deal with every possible combination of those non-terminals, and that doesn't necessarily make it easier or faster. So in general, we just only want to substitute if we're between terminals.
It's because the terminal on the right-hand side guarantees that it will end, and you can just like, in these three steps, just like push it all into the original.
Yeah. Yes. That makes sense? Anyone have questions on that?
I think so. I mean, you're basically just sort of expanding in place. the
Yeah.
Evaluation of the other production rule.
Yeah.
Right? Yeah.
That's,
Has a similar vibe to regular expressions, I think.
yeah. So, yeah, at the end of this, the B production is no longer necessary and just go away. Sometimes you want to remove unnecessary productions, and this is something that is very useful. So here is a grammar. What do we notice about this grammar?
The capital A. Could be redundant. Oh, wait.
There's an empty string inside of it, so
That's okay. That just means we accept the empty string and anything.
Just two guys. AS.
S to AS. To here,
Replace A's production in S.
replace this
Yeah, S.
with just S.
Yes.
Yeah.
AS. It turns out that A can't ever terminate. Once we choose this production, can we ever reach a point where we have something, a string in the language? It just says produce another A, produce another A. It's the equivalent of an infinite loop in programming, where maybe you're printing a single character inside of that loop, but you're never going to stop, terminate with a particular output. So S arrow A arrow. Now we're going to create an A and loop to an A. This A can replace with A, capital A, and that's the only thing it can do. A, capital A, that's the only thing it can do. This process will never terminate, and we're never going to see that there is a string in this language with a bunch of A's. It just generates A's forever, never terminating. So the question I would have is, what is the point of including the A in the grammar? Does that non-terminal define any strings that are in the language? Does any string that's in this language go through that capital A and utilize that portion of this grammar? If we strike this out of the grammar, does this represent the same language as it did before?
Yes.
Yeah, it does. There are no strings in this language that went through this process because we would have gotten into this infinite loop. So because of that, there was an unnecessary or a useless production in this grammar. So we're going to define the concept of useless as a non-terminal that is never part of any string derivation that's in the language. So I defined a useless production, but a useful production appears in at least one derivation for some string that's in the language. And then a useless production has a useless non-terminal. Non-terminal is not used to derive anything in that language through any sequence of productions. And any useless production can be safely removed from a grammar without changing the expressivity of that grammar, which language that grammar accepts. Ready for a practice problem? All right. Here's a grammar. Make this as simple as you can, removing unnecessary garbage from it.
this is sure.
Yeah, if it clicks, this is one of the easier practice problems in my class.
This will be on the test, right?
Maybe.
Like this specific problem. Please.
I can hope.
I've had professors where they take homework problems, just throw them around and leave it in,
Oh, yeah.
like the brick.
I have been known to do that for not homework problems, but things that are on the homework document. That is one of the practice problems.
Like do number 7, A, B, C, and then you give us like D and E.
Probably not D and D, but I might give you, if it's like A, B, and D, I might throw C on the exam.
Right.
Now you're making it really hard to just do the required question.
I'm not stopping.
Yeah, I'm just saying that if you have the extra time or you feel like the extra practice does you good. Maybe something eventually in the class will seem familiar to you. Like you've solved it before. And then maybe I'm especially evil and just change one letter or change one little thing about it. So it looks like something you've seen before, but it's slightly different. Always use critical thinking.
Jokes on you, I always look at every single problem and analyze it much, because I cannot remember what I did last night.
I would be the kind of professor who, if I had multiple choice on any of my exams, I would force the answers to be like A, B, C, D, A, B, C, D, something of the sort, where every answer is a C.
I've never had that happen, but I've had professors tell me about it.
Yeah.
It just feels wrong.
Right, it's like, there's something wrong here. And then halfway through, I would switch it up so that anyone who starts to notice the pattern and just like, all right, well, everything has to be C. It's like, no, you got you.
Even if you see the problem, you don't know if it continues, so you have to like keep
Right,
doing it.
right.
Or even the multiple choice question will be which multiple choice right at the very end is just the looming, none of the above.
Yep.
Funny that, yeah, all of the above or none of the above is
Yeah.
more frequently than it should be the correct answer to a multiple choice question, which is kind of annoying.
My favorite is like which of the above statements are true.
Yes.
Like A, B, and C. C and E. Only B, you know. Those are.
If I did multiple choice questions, I would phrase them like that, except make you tell me which ones are true, and which ones are not. So that way you would have to,
Yeah.
that you can also get partial credit on. I don't like designing any questions where people can't get partial credit for partial understanding. That just bothers me.
Yeah.
All right, what did we do?
I push the A production into X.
Yeah, so we could end up substituting as well. Yeah, so C creates an infinite loop. B is never a non-terminal on the right-hand side of anything. So we have no path through B in any capacity. And then we could easily substitute A back up into the S production to make it simpler as well. So you can envision this as kind of a directed graph problem, or kind of like you would draw a DFA. And we see that there's no way to reach B. So we can safely eliminate B just because it cannot be reached from any path starting at S. So it's underlying a graph problem, a graph traversal problem. But yeah, C is an infinite loop, so we scrap this because it's part of no string that is accepted by the language. It's a useless production. B can't be reached, and A is a really easy substitution. If we just throw this A back up in that place. So we basically get, this is the equivalent to just S arrow A, S, or A. Which is kind of a stupid language when you think about it. But you can also make an arbitrarily complicated grammar that represents that same language. And I think that's kind of funny to think about, how you can just blow up a grammar with useless garbage. And it represents the same language as this very simple kind of useless language.
Like Windows.
A single A or more A's, and the language of any number of A's. Except 0 of them, we don't accept that. Screw 0. People who think natural numbers start with 1 invented that language.
Yeah.
And we did it. It was just about a little more than 10 minutes, that slide deck, but just wanted to kind of briefly talk about how to take the complexity of grammars, and if there's useless complexity, strip off that useless complexity. Did not think that we would get to the next one, so I actually have to go grab it. We're getting to the fun stuff. The fun and reasonably complicated stuff inside of context-free grammars. Before we get into, you know, the not so fun and complicated stuff like the extension to the pumping lemma. This is the more fun part.
When we take Exam 2, is both the original pumping lemma and context free gonna be on there?
We won't quite be to that point yet, I don't think. There's still a lot of context-free to cover. So we found that every grammar that can recognize a context-free language could be converted. We will see that they can be converted into other forms. A simpler form we have seen, but there are a couple of normal forms that are useful for certain kinds of computation. So yeah, some of them have been standardized and are commonly used when we do create grammars for specific purposes. One of them is to answer the membership problem. So we are going to learn about 2 of them. The first is Chomsky normal form. Noam Chomsky was a huge part of computer science history. If you don't know too much about him, he is responsible for a lot of formal verification in software. If you ever want to be able to prove that your software is performing the way that it should, and you don't want to write an infinite number of unit tests, you can use a concept called formal verification, and Chomsky was the father of a lot of that math.
You know Chomsky's first,
No,
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 I thought you said normally for a second, I was like.
no, like a garden decoration. That's why.
But I thought it was funny because I was like. I mean.
Noam Chomsky. Yes, so as long as we can strip out the empty string and or lambda from a grammar, which we can always do either via substitution or via factoring it out as the empty string representation as we showed in the last slide deck, then there is an existing grammar in what we're going to start calling CNF, Chomsky normal form. And what this is going to do is restrict the number of terminals and non-terminals that we can have in a particular production, and it's going to bloat the number of productions that we have. So we're going to go from complexity in individual productions to just lots of productions. And each one of those productions is going to be very simple in nature. What's beautiful about this is the conversion is actually really easy. Once you understand how this is done, then there's not a ton of complexity to it. The second one we're going to cover is Greibach normal form. And just as in CNF, if there is no lambda in the grammar, there's an equivalent in GNF. And this just places restrictions on the positions of terminals and non-terminals with respect to each other. And each of them are used for something different that we will talk about throughout the course. We'll spend a little bit more time on CNF than GNF. GNF comes back in one piece when we're talking about a specific kind of conversion that we will go through. The GNF conversion is not straightforward. So we're not going to ask you, given a grammar, convert it to GNF. We will just give you grammars in GNF. But conversion to CNF is really easy. Yeah.
So this is any safety without a lambda grammar. Does that also include those top statements which say this can accept the empty string? Is that included in that?
It's not, because you can make turn this into CNF and then just have that rule on the outside that says we also accept the empty string. And then wherever you have an or empty string, you can use substitution to move that upwards and get rid of the lambdas in the grammars. It becomes one of the easier substitution rules. So we can remove lambdas from grammars and keep them equivalent. But we will have to come back tomorrow and learn more about CNF. And as we dive into how to actually answer the membership question in better than exponential time, which is very exciting, has very exciting theoretical results. And it's used in compilers.
A lot of people. Play math, figure this out.
Yes, very true.
Figured out.
Chomsky dedicated a good chunk of his life to all of these results. So I have office hours starting now because I don't have my next class. So if you have any questions on homework, I will probably get out the next homework because that is due, the current one is due tonight. And I'm gonna get out the next one for next week. Yeah.